We're ready for the second part of the evening. For the second talk, we have Kevin. Kevin comes from Colombia. Welcome. And is going to tell us about AI and auscultation. Please welcome Kevin.
Thank you so much. Can you hear me? Can you hear me? Yeah. Okay, perfect. Good evening, everybody. Tonight I'm going to talk about AI and auscultation. I'm going to show my participation using Python in a very promising idea of innovation in the medical industry we have been working from Colombia. Oh, wait. Okay, I'm going to start my presentation by introducing myself. After, I'm going to talk a little bit about some background information. I'm going to talk about the problem. I'm going to talk about auscultation and the stethoscope, what that is. And also, we cannot talk about these two things without introducing the heart sound and how does it look like. I'm going to talk also about WORDS initiative, what researchers in different places around the world have been working in this same topic. And after, I will talk a little bit about my project, the development of algorithms to analyze heart sound signals. And at the end, I will talk a little bit about some summary. Give me 1 second. Well, it's not working. All right, this is me. I'm Kevin, as I say. I'm from Cali, Colombia. Please do not think about Cali cartel or any of those stuff, Narcos and Netflix. Cali is a really nice city in Colombia, located at the southwest of the country. And I know all of you, or many of you have watched the World Cup. And it's very easy now to remind us by the Colombia football team. We almost won, almost. I am a biomedical graduate student from Universidad Autónoma Occidente, nice green university in Cali. And a biomedical engineer, it's simply a person who learned from medicine and engineering to try to apply solutions to solve medical issues or health problems. Right, so after I finished my undergraduate studies, I decided to join, or I wish I can join a group of people and start developing real case solutions in medical problems. So I make a proposal to Dr. Reynolds Pombo, and I started working as a volunteer research assistant in the cardiovascular medicine and specialties of high complexity research group in Fundación Clínica Chayo. It's one of the best hospitals in cardiovascular diseases in Colombia. And it's directed by Dr. Jorge Reynolds Pombo. Actually, he's Middle Colombian and Middle English. This Reynolds have developed one of the first pacemakers in 1958. This was very inspirational for me. And since then, he has been a pioneer in pacemaker technology. There, I have been working with recording heart sound signals from healthy patients, mostly, in order to analyze how or which patterns we can extract from healthy patients with healthy heart sounds and see how we can create a signature of the heart sound in this type of patients. And that's mostly what I have been working over there. So what's the problem behind this research, or why is this important? You will see. Cardiovascular disease is why this research is very important. According to the World Health Organization, cardiovascular disease is the leading global cause of death. In Colombia, for example, cardiovascular disease causes the 29% of all deaths in the whole country. In the UK, 26% of all deaths corresponds to cardiovascular disease. Actually, the difference is not really big between the two countries. 80% of all cardiovascular deaths are caused by heart attacks and stroke. And the most important thing is it's been projected by 2030 to cause more than 22 million of deaths every year. So this is alarming, isn't it? Now, one of the first steps doctors uses to analyze the cardiovascular system is the auscultation of the patient, right? If any of you have been in medical consultation, the doctor normally takes his stethoscope and analyze the sounds or the heart or the lungs, which are the sounds inside your body. So let's talk a little bit about what's auscultation and what's the stethoscope. So as I say, auscultation is the action of listening to the sounds inside the human body. This could be the heart sound, the lung sounds, the abdomen, for instance. Auscultation is being reported a long time ago, the 5th century BC, by Hippocrates. He was a doctor. He used to use his ear to listen to the sounds inside the human body. But nowadays, auscultation is being performed by a stethoscope. However, the stethoscope has not always been as now it is, and I'm going to show that. This is the first invention of the stethoscope, invented by Dr. René Laennec in 1819. It was made by wood. It was monaural, which means the doctors were able to analyze the heart sound with one ear or the other. Years later, Dr. George Kamen invented the first binaural stethoscope. Doctors were able to analyze the heart sound and to listen to the heart sound with both ears. Almost a century later, Western Electric developed the first electronic stethoscope. Now doctors were able to listen to the heart sound and control the volume, and even apply analog filters in order to listen to the heart sounds more clearly in different bands. Nowadays, doctors use the classic Littmann stethoscope invented by Dr. Littmann in 1961. And the stethoscope itself keeps changing. There has been more technology being applied in the stethoscope, and now we can find in the market, in hardware speaking, a stethoscope with the capacity of sending the heart sound signal to a computer to be able to analyze the heart sound and even send the heart sound signal to another colleague in a different country. So this is very interesting. Inventions are not made just by a single person. Inventions are contributions for people in different parts of the world. So it's important to see what world's initiatives have been doing. One important thing is to realize that people who are not able to have access to heart sounds, they are not able to find public databases in order to start developing algorithms to classify or process the heart sound signal. One of those public databases I really like is provided by Physionet. They also provide different type of physiological signals, including heart sound signals. They have more than 4,000 recorded heart sounds from healthy and unhealthy patients, and this is a very important contribution to people who is trying to work with heart sound recognition. There are also more databases as well, but the one I really like is Physionet. This is very important, I think, very important achievements. Researchers in different countries, actually, Houston, Texas, and, well, Denmark. They have been working and investigating using a digital stethoscope, analyzing the heart sound in healthy patients, and also analyzing the signature of the heart sound in patients with coronary artery disease, which is another type of cardiovascular disease. And they have found differences induced by this stent placement. Sometimes when patients have coronary artery disease, they require a stent placement, and they have found differences induced by this little device in the heart sound. And I think this is a really, really important achievement and when talking about this kind of technology. Because if we are able to analyze or identify differences made by these devices in the heart sound, it could be a really nice approach if we keep doing research and with these signals. So that's an important approach. Also, it's very curious how algorithms that have been applied in image recognition or artificial vision are also being applied in the heart sound signal. Basically, researchers, by transforming the signal from amplitude and time domain to frequency domain or Mel coefficients, are able to apply vision recognition to classify the heart sound signal as pathological or non-pathological. And I think that's also very interesting. Now, going to introduce what is a heart sound. Before explaining this image in the right side, I will play a normal heart sound a bit. So if you, wait, that is. So there is a dun, or doctors call this lupdub, right? This lupdub, we call this lupdub the two principal components of the heart sound signal, and we call it S1 and S2. Physicians, in order to make the diagnosis of a patient when they are performing the auscultation procedure, they need to listen very carefully to these two segments and identify, they need to identify abnormalities between S1 and S2, and also abnormalities between S2 and S1. And then this gives information to the physician to, in order to classify the heart sound. So that's a very quick explanation of it. Now, what have been working on using Python? Okay, first thing, I know this is not PyData London, but the first task I needed to work on was to pass some algorithms from MATLAB to Python. And well, it was very easy. It was not difficult. There are lots of tutorials out there people can use in order to work with Python and start programming with Python. So first challenge was to develop an algorithm to perform the segmentation of the heart sound. As I say, as doctors needs to classify the heart sound and separate S1 from X2. We did the same. We develop an algorithm which works very well. As you can see in this graph in the third row, these are classifications or identification, sorry, of each of the segments. That was the first task. Second, we have been working with signal processing techniques in order to develop digital filters in Python in order to analyze the heart sound signals in different bands, low, medium, and high frequency bands. Could be others. I will play a little bit this song so you can appreciate the differences. So this is a heart sound in low frequencies. Normal, right? And this is in medium frequencies. Now, high frequencies. This is very important because we can extract information within the signals, analyzing different bands, and use this information to feed machine learning algorithms to classify the signal. We have been also using fast Fourier transform to transform the signal from time domain to a frequency domain and analyze the frequency components in the whole signals and each segments of the signals. We have also worked with the spectrogram in order to analyze the variation in frequency and time, and I will show in the next slides. So this is a non-pathological heart sound. When the doctors are using the stethoscope, they are not able to view anything in the signal. They just use the capacity of listening to classify the signal and to give their diagnosis. And it's very interesting how how it's being introduced a picture of the heart sounds in order to give more information to the physician in order to better classify a heart sound. This is how it sounds like. The image above is the spectrogram, frequency over time, and the image below is the phonocardiogram, amplitude versus time. And we can, for example, we can see in the second graph how it's a normal distribution, and we can also see like the S1 and S2 components normally. And also, these components creates signal in the frequency domain, which goes from low frequencies to high frequencies constantly. Now, let's analyze, or let's see how it looks a pathological heart sound. And let's listen to a pathological heart sound. Well, there's anybody able to tell me if he can differentiate an abnormal from the normal heart sound just with the sound? Is it clear? Yeah? Okay. Well, there are heart sounds which are not very clear to identify, and in these cases, we're not able to use images, which gives a little bit of more information in order to classify these heart sounds. So that's a really nice approach. All these animations are being made also using Python. And well, I am not allowed to talk too much about these approaches since we published. But we have been also working in biological inspired algorithms. These are neural networks inspired by the human brain, specifically in the auditory system, where utilizing or using some of the structures in this part of the brain to develop our algorithms, our neural algorithms. And we have been able to classify, to identify the segments S1 and S2 automatically, just passing the whole signal through the neurons, and the neurons, one of them, are able to fire when it's when we have when they identify each of the segments, S1 or S2. All right. Any of you have been working with Qt? Good. Well, for those who say, who raise their hands, Qt is a very nice platform to develop not just graphical user interfaces, but also to show their visualization techniques. It's a very nice platform, and it has a lot of libraries with Python in order to either develop graphical user interfaces from Python or directly from Qt. We have been working on how to show to the physicians the information, because it's also important not just to say this is an unhealthy heart sound or a healthy heart sound, but also to show the information so the physician, it's the one that takes the decision make the diagnosis of a patient, right? So it's been very important for us to develop a prototype of graphical user interfaces to show the information to the physician. So to close, I think AI, it's also moving to the auscultation specifically, and these approaches are being shown that it could help physicians to better take their diagnosis using different techniques. In the hospital, we have been working, trying to create a signature of a normal heart sound in order to better classify the heart sound signals in patients. Also, it is important, and this is kind of a race, because there are many people around the globe working in this same topic, and the computer interaction between the machine and the doctor, it's a very important challenge, because doctors are very skeptical about using this kind of technology, because, well, this idea that the doctor is going to be replaced by the machine. But I think doctors should use it, should embrace artificial intelligence and this kind of techniques in order to better develop, to drive health. How do you say that? Doctors should use this kind of technology to better develop their procedures, and they need to see this as a tool and not as an enemy. Okay. Right. So some of the things I can show are here in my GitHub account. This is a library, an open source library of algorithms. I developed this with my friend Nicolas, and well, this is free for everybody interested. That's it.
Thank you, Kevin. Questions? Time for a couple of questions. Over there, yeah.
Hello. Hey, hello. Great talk, thanks very much. Really learned a lot about that. I was wondering, you showed this new stethoscope, right? That the electronic one where you can send recordings of heartbeats around. Do you know if there's an effort also to kind of collect that data and kind of move it to this PhysioNet and kind of improve the data set as it's available, or is that not yet done?
Like if it is a, well, what I know is the PhysioNet, they have different research groups that have been contributing with more heart sound signal, and not just heart sound signals, but electroencephalography or electromyography signal, different type of physiological signals. And these research groups, mostly located in the US, PhysioNet and FusionNet also have different challenges, and they already have their partners which provide these signals. Now, well, this electronic stethoscope is it's been released by Littmann. I don't know anything about if Littmann has a kind of contract with them to try to provide these signals. This Littmann stethoscope is being used by private doctors, so I don't know if they are also able to share the information from patients. That's a really a specific thing. I don't know.
One more question, yes? Hi. Microphone, please. In front of you. On the seat in front of you, there's a microphone. Need to switch it on.
It's good to see you doing this data, but it's, I mean, I have two questions. One is, have you developed a model of a beating heart, which you can then sort of test your algorithms on?
A model of a BT heart?
Yeah, so like a mechanical model.
Oh, okay.
So it's made up of various components which replicate the cardiovascular structure, and then you have blood, which is the fluid flowing through the various valves. I was just wondering if anybody has done that, so that you can actually then introduce known pathologies into your model and then see how it affects the heart.
Yeah.
Or the sounds. The other question was, should we be listening to our heart sounds from day one? Because all we need to do is to find out whether it becomes abnormal from our own reference point.
Sorry, I didn't catch that.
Have you thought, we have iPhone, have you thought of having an app where we record our heart sounds regularly while we're asleep, and then it tries to pick up of any abnormalities that are coming through as our pathology goes downhill?
Okay, I got that. Okay, the first question, no, I don't know any model which replicates the heart sound, but that's very interesting. So no, I haven't heard about that. The second thing, there are different devices. Actually, Apple has in some of their phones an app capable to measure healthy parameters from their users. And I know that one of them is the heart sound. But I think this should be more in hands of the physicians and not the actual patients. Because, well, I imagine if I am able to have a phone that can tells me when my heart sound is good or not, if I have the power of that technology, well, I will be running all the days to the hospital and tell her, hey, doctor, look, my app is telling me my heart is not working properly. And, well, I think this will be a little a kind of crisis. What I think, it's the signals should be sent to private doctors. Now, I don't know if any of you have heard about Babylon. So this company is working with doctors online, able to make diagnosis with the patients online. And I think this technologies should be articulated with this kind of infrastructure instead of just giving the power of analyze your body by itself. I think that's my opinion.
Sorry, we should wrap it up. We're running out of time. Will you be around for the rest of the evening at the PyData? You can continue the conversation with Kevin later. Let's thank Kevin one more time.